So, a lot of things to do this week. The big thing is we've got the exam coming up on Thursday. We've got a Mastering Chemistry assignment due on Wednesday. The way that we're going to accomplish this is we're going to finish up the notes on today, and we'll use about probably a class period's worth of time on Tuesday. And then we can spend some of Tuesday afternoon working problems at the end of the chapter, and then we can do Wednesday student review. Okay, test on Thursday. Any questions? All right, remember this Mastering Chemistry, 18 problems, you need almost 2 hours on it, so don't put it off. And I know several of you have lots of room to work on it. So we're going to continue talking about equilibria in chapter 15. And the last thing that we talked about in our notes was looking at this clicker question with how to calculate a value for an equilibrium constant K sub C. Now we're going to continue this just a little bit, looking at a different aspect of it. And that's what if how we deal with everything not being in the same phase. So we talked about this a little bit with our end of chapter problems and kind of started this a little bit last Tuesday. But if we have a heterogeneous system, so that we have multiple phases other than just our solution reaction. So that means if I see solids in the system or if I see pure liquids, what happens is their concentrations don't change during the course of the reaction. So if I see those substances, that means that they don't appear in the equilibrium constant expression. So if we look at this example, CO2 gas plus water in the liquid state yields the hydrogen ion and the bicarbonate ion. When we write out the K sub C expression for this, products over reactants, it's products, which is the hydrogen ion, the bicarbonate ion, and then if I look at the reactants, the only reactant I include is the concentration of the CO2, and the Y is because water is a pure liquid. Okay? And in the solvent phase, its concentration doesn't change. Water is always 55.5 molar. So anytime that I see a solid after a substance or a pure liquid, represented by L, that means that it doesn't appear in the K sub C expression. So it's not in the K sub C expression. Okay, so we're going to look at some examples of that. So if we had a generic reaction, A plus B yields product C plus D. And if I want to write the equilibrium constant expression, I need to put it as products over reactants, but I will need to look at the phases. So starting with the products first on top. If it's an aqueous system, D is in the aqueous phase, so it's going to go on top. So little d, or big D to the little d power. The reason the C doesn't appear is because of the liquid phase. It's a pure liquid in this system. So this is going to be a biphasic system. Actually, it's a triphasic system. And then if I look at the reactants that would go on the bottom, the reactant A is a solid. Because it's a solid, it wouldn't appear. Only thing I'm concerned about are the things that are in the aqueous phase. So the reactant is going to be little b, or big B, to the little b power. And that's my K sub C expression. And anytime you have it where all of the reactants or all of the products are not in the phase that you're describing, you can put it 1 over whatever the products are. Oops, sorry. Do that again. Products over 1. If all the reactants are solids or liquids, or you can do the inverse, 1 over the concentration of the reactants. If all products are liquids or solids. Okay, and it would just be the products if The things that are solid are the reactants. Yeah, so if we don't have a concentration to put in there, we just use a 1. So in this example, we use 1 and 1 to represent those two different concentrations. Question on that?
Which is the one we don't count the liquid? It's like when we don't use the liquids, we just use the solid and the aqueous.
Well, you just use the aqueous. So you're not going to use the solids or the liquids, pure liquids. Just use the things that are in aqueous. Now that's assuming an aqueous solution. If I dissolve something in acetone or ethanol, that becomes my solution. But most of the things that we do, we describe it in terms of an aqueous solution. So here's an example of just a demonstration. Now we can see this and see that this dependency on the equilibrium is not dependent on a solid. So if we look at the heterogeneous equilibrium that exists between carbon dioxide in equilibrium, or carbon monoxide in equilibrium with CO2 and pure carbon. So a lump of coal sitting there. So it doesn't matter how much carbon I have in this vessel, okay? Whether I had just a little bit or if I have a lot, as long as there's any carbon present and the system's at the same temperature, it's independent of the amount of carbon. The amount of CO and the amount of CO2 are going to be the same in both systems. They don't change. And the way I know that is I've looked at the K expression for this, products over reactants, and I put my products on top, the CO2, reactants on bottom, the CO, because of the 2, I have to square it. And because this is in the solid phase, that means that it doesn't appear in the equilibrium constant expression. And if I wanted to write a K sub P, it's the same way. Instead of K sub C, because it's a solid, you don't have a pressure for the solid. Okay? It doesn't appear there as either. So it doesn't matter if I fill this jar up with carbon all the way to right here. It's still not going to shift that equilibrium concentrations. Or if I take everything out so that there's just one speck of carbon solid left. So if I got rid of all that and had one little speck of column, as long as there's any solid present whatsoever, the equilibrium is not dependent on that. Now, if I got rid of the solid, then it would shift. There's just got to be some solid present. Okay? But it doesn't matter how much. Okay? Easy enough? Just remember to look for the phases. Okay? Look for the phases. Products over reactants. Answer it on your own. 2 more. Okay, all in. 2 predominant choices. So we either thought it was A or D. Let's see if we can think about that, figure it out. All right, so A says that it's products over reactants. And then it's got the KCl as a product, and you got the O2 as a product. All right, so if I look at the phase of the KCl, it's a solid. Because it's a solid, it doesn't appear in the equilibrium constant expression. So that tells me it's not A. If I look at D, the other thing that was choice, it's products over reactants. I'm going to have the O2 to the 3rd power because of the 3 stoichiometry. I've got that. And if I look what I have for the reactants, the only reactant I have is a solid. Because it's a solid, it doesn't appear in the expression. Choice D.
If it would have been the reactant, would it have been 1 over?
That's correct. Yeah, if it were flipped around the other way, it would be 1 over that. And we will run into calculations like that where we have to set them up. All right, question on the why there. Always look at the phases. That's when you're looking at these expressions, that's absolutely critical. And I think I told you all this, when you do the mastering chemistry, you got to be sure to put the phases in parentheses or it won't accept your answer. So you've got to make sure to put those phases. But a lot of times when we write equilibria out, we know everything's in solution. We don't write that it's in a different phase, just to save time. But mastering chemistry is absolutely looking for that. Okay, so what we want to do now is we want to take and calculate what are the equilibrium concentrations of some products or the reactant, as long as we can measure something. So we're going to take one system or one component that's going to be measured, and we're going to apply that to everything else to find out what the unknowns in the system. So the best way for finding the equilibrium constants is to measure the amount of the reactants and the products that are there at equilibrium. However, it's not always convenient to monitor the concentration of every species. But what happens when an equilibrium mix, you may have different amounts of products and reactants. The equilibrium is going to adjust, but that system at the same temperature is always going to have the same equilibrium constant to be achieved. So as long as you don't alter temperature, the K value, K sub C, is going to be the same. So K sub C doesn't depend on what are your starting concentrations. Right? It doesn't depend on the initial amounts of the products or the reactants. It just matters what it is for that particular temperature. And here's an example of that. So I've got my arrows went in the wrong place here. I don't know how that happened. I hope it didn't happen in your notes. So hydrogen gas plus molecular iodine form two HIs at 455 degrees Celsius, and it gives us some reaction conditions. So if I start off with just the reactants, 0.5, half a molar of each, and there's none of the product. When the system reaches equilibrium, there's 0.11 of the hydrogen gas, 0.11 of the I2, and it's formed 0.78 of the product HI. So if I do products over reactants, everything's in the gas phase, so I can use those. So I take the concentration of the product and square it. So that's going to go up here. That needs to go on the outside. All right, so HI squared divided by the concentration of the H2 and the I2. So that's going to be the value for K sub C. So if I just plug in the numbers for those, the 0.78 for the HI, square it. The concentration of the reactants that's remaining, 0.11 and 0.11. If I square it, divide those out, it's 50. That's the value of K sub C. Now, if I looked at the system in the other way, I'm just going to start now and start with just products. All right, so I'm going to start with just the HI. So if I take my container and I put in 0.5 molar HI, there's none of the reactants, and I let the system run to equilibrium, what happens is the reaction has no choice but to go in the reverse direction. It has to go that way. But in the process of doing that, it makes 0.055 moles of H2, the same number of moles of I2, and the concentration of HI is decreased from 0.5 to 0.39. Now, if I plug those concentrations back into the same K sub C expression, products over reactants, the products squared, there's my products, the reactants, each one of those, plug it in, divide it out, I get the same value of 50. Okay? So let's do a third case. Let's look at starting with some mixture. So on this one, I'm doing 0.5 moles of both the reactants, every reactant, and the products. So on this case, the reaction goes forward because the reactants decrease in concentration. They decrease from 0.5 to 0.165. The other one's 0.165. And the products started at 0.5, now have increased to 1.17. If I plug it in the K sub C expression, products over reactants, products squared, reactant, these two, do the math, it's still 50. That's a good thing about chemical equilibrium. It doesn't matter where you start, what you have, the system's going to go to the same point of equilibrium every time. Okay, so it doesn't matter, and there's two other examples at the bottom with different concentrations. Things don't have to be the same. This one, you've got twice as much as the first reactant, H2, as you do the second reactant, still comes out the same value of Kc. You swap them around, now you've got twice as much as the second reactant, still got the same value of the equilibrium constant. So it's dependent simply on the ratios of the concentration raised to their power. It doesn't matter what the starting is. The system's going to adjust until it reaches the ratio being 50 in this example at 455 degrees, 445 degrees every time. If I change the temperature, I change the value of that K sub C. Okay, we'll talk about how to look at that later. Okay, so I'd like to know, how can I calculate the concentrations knowing how these things are going to respond, and K sub C is now a constant in my system. So what I use is the stoichiometry. Those are the coefficients in front of the balance reaction to determine what the concentrations are for all the reactants and all the products, given that I know the initial concentrations and I know at least one product or one system, either product or reactant, at equilibrium. I have to know, could be a product or could be a reactant, what is the system when you reach equilibrium? So if I monitor one species, I can relate the change in that species to everything else in the system. I'll show you how. We use a table called ICE, so that stands for Initial Change in Equilibrium Concentrations, to fill in the gaps, what are the missings, and we look at the change in the concentrations for the thing that we know to establish the change in concentration of all the other chemicals. This is about as critical thinking as it gets. You got to put all the little pieces together. But it's really just dimensional analysis. Okay? It's looking at what's going up and what's going down and what is the mole ratio between those things. When you approach it like that, it's not that bad. All right, so here's the example of a system where we know this reaction. I've got 2 A's plus B yields 4 C's. And the initial concentration is I have 1 molar A and 1 molar B, and there's no C initially. And it tells me at equilibrium, the concentration of C is measured at 0.5 molar. So initially I didn't have any of it, and at the end I have 0.5 molar. So what the I stands for is the initial change in equilibrium concentrations. So if a reaction goes forward as written, and we'll find that reactions as written don't always go in the forward direction. That's the reason we have the arrows going both ways. But if it goes forward in the written direction, this one doesn't have a choice to go in forward because there's no products initially. It can't go backwards. It has to go in the forward direction. So that means I'm going to expect this number to increase and the amount to change for the reactants to be decreasing. Okay? They should be going down. So I know at the end I've got 0.5 molar of this product, and I know initially I had 1 molar and 1 molar, and there was 0 of the product C. So what I want to do is figure out what the change is. So the way that I can do the change is simply look at the stoichiometry between the products. So I know the balance reaction is 2 to 1 to 4. So the same way that we've done mole conversions, all through GenChem 1 and GenChem 2, I can take that I've got 0.5 molar of C. All right, so we can get my M in there. I've got 0.5 molar of C. And if I want to relate that to A, all right, so if it changed to be 0.5 molar in C, the relationship between C and A is that there are 4 C's consumed, 4 moles of C consumed for every 2 moles of A that react, or 4 moles produced for every 2 moles that are consumed. So if I look at that change that's going to occur, I've got the 0.5 times 2 divided by 4 that's a 0.25. And since this change was positive, I know this one is on the other side, it's going to be a negative of that. So it's going to be going down 0.25 molar. So the change is a minus 1/2 of the change that occurred on C. Now here's where you've got to decide what works for you. If you can see this in your head to say, know that this is a minus 1/2, you can just see that, me and my eraser. If you can see that this is a minus 1/2, and that's clear to you, that's going to be minus 1/2 of this initial, you don't have to worry about setting up this mole ratio diagram. If it's not clear to you why this is a minus 1/4, set up the mole ratio diagram. Okay, so do the factor analysis on it. In a similar fashion, if we were going to look at what's happening with the other reactant. So now if I look at the changes, 0.5 molar increase as C. And if I look at the ratio between C, there's 4 molar of C that are produced for every 1 mole of B that's consumed. All right, so on this one, the change is going to be 1/4 of that value. So the change would be 1/4 of 50 is an 1/8. It's going to decrease by an 1/8 molar. That's where that's coming from. So I simply take what was the initial concentration. This change was 1/4 of a molar. Less the change, and it tells me the equilibrium is 0.75. And then I can look at this initial was 1 molar. The change was decreased 1/8 molar, so it's 0.88 when you round. And then if I finally look at the last one, this is the one I knew to start with, so it was given in the system. I can take one thing that's measured and relate it to everything else. This is what the ICE, what we're trying to accomplish when we set up this ICE table. They take practice. That's the only thing I can tell you. If you get stuck and you don't understand what to do, my advice is to go back up and look at this stoichiometry. You simply look at the ratio of the number of moles. Okay? And you can do that to help solve the gaps in these tables if you can't figure it out. All right, I'm going to do a lot of examples for you. All right, here's another one. So I'm going to take this one, I want to find the value of K sub C, and I've got 2 methanes, CH4, yields acetylene, C2H2, plus 2 hydrogen gases. All right, and this is occurring at 1700 degrees, and I know the initial concentration of the reactant, and that's all I have is a reactant to start with. And at equilibrium, I know the amount of one of the products, the acetylene, is 0.035 molar. And I want to find out what is the value for K sub C. So this is the thing that I'm looking for. To find K sub C, I know I've got to find the values for the products, and the reactants. Okay, so what do I know of those? So do I know anything in this? The only one I know initially is this guy. I know that. Okay, I've got to figure out what these other 2 concentrations are. So we're going to go to the ICE table and figure that out. So what I know is my initial, and my initial is the 0.115. It tells me the initial concentration, and I don't have any of the products. And it tells me at equilibrium that I've got 0.035 of the one product, so that means it had to increase by 0.035. So now this is where I can use the stoichiometry to figure out how much of the other products are either being consumed or produced. I know that this reactant is going to have to decrease, and I know this product, since there wasn't any, it's going to have to increase its amount. It's going to have to go up. Okay, so we'll start trying to figure out the holes. So if I look at the stoichiometry, we'll go back and I'll write these out the long way so we can maybe all see it together. The one that we know the concentration of the C2, so we had 0.035 molar formed of C2H2. And if I want to relate it back to this reactant, if I look at the mole ratio, 1 molar C2H2 forms from 2 moles, 2 molar CH4. So if I look at that change it's going to be 2 times that concentration, so it's going to be a negative 0.70 molar. So that's going to tell me how much this guy is going to decrease by. All right, so that's what we see exactly in the table. If I go in and put the value for that, it's negative 2 times that times the change in concentration that occurred for this reactant. So that can tell me if I subtract that, the concentration of the methane is 0.045, and I do a similar thing for the other reactant. All right, so on this one, I know that for every methane or acetylene that's formed, there's going to be 3 hydrogens. So if I want to set it up with the C in the stoichiometry, let's do it that way. So I've got 0.035 molar C2H4, and there is 1 molar C2H2, sorry, I said 4, or 3 molar of the product, H2. So on this one, I'm just going to multiply it by 3, so 0.105 molar H2. So this one is going to go up by 0.105 molar. And the fact that it didn't have any initially tells me it's going to be 0.105 molar. Okay, so if I look at the value of this one in the table, that's where that comes from. All right, the 0.105, it's simply a bad color choice. Top of blue. It's simply 3 times this initial concentration, 3 times. So now I know all these concentrations at the bottom. I can go back to my equation that we had to start with, just simply plug in the concentrations for each one of the species, take them to the respective powers, the cubed for the hydrogen, the square for the methane. I take the acetylene concentration, plug it in, the concentration of the hydrogen, plug it in and cube it, divided by the concentration of the reactant methane, square it because of the 2, and I find out the value of K sub C is 0.02. Okay, that's a lot of plugging in the pieces.
So on the exam, will there be a chart? I mean, and then we have to like fill it in and then get that case.
Usually you're going to have to make your own chart, and I'm going to show you how to write those out as we go. There will be some cases where I give you a table and I'm going to ask you to fill the missing thing in.
That's all.
Okay, so you'll see both of those types of problems if you start looking at the old exam. Okay, good question. All right, let's do some of these. All right, let's look at another one. Here's one where it's the table. All right, fill in the gaps. So on this one, I want to got the reaction of 2 NO2s yields N2O4, dinitrogen tetroxide at 100 degrees Celsius. And we'll just do, it wants to know K sub C and K sub P. And there's 2 sets of experimental conditions here. And they're both independent of one another. So we're just going to think about one first. Okay, so on this one, initially I'm starting with this reactant, and there's none of the product. And it tells me once the system's reached equilibrium, what happened is this one has decreased to this amount. Okay, so if I were going to start this from scratch, let's talk about how we would do it like that. Get the blank page there. All right, so pen. Okay, so my reactions to NO2s, all right, yields. Let's start with writing my reaction out. 2 NO2s. Your fans in the gas phase. Yields N2O4. All right, so now I've got my reaction. If I look at the way that we write the ICE, I stands for initial, C represents change, and E represents what's the concentration going to be at equilibrium. Okay, so what we know in this one is we know the value of the reactant is 0.0127. All right, so we know that its equilibrium concentration is 0.0127 molar, and it told us something about the initial concentration is 0.02. All right, so the initial concentration was 0.02 molar. Now, there wasn't any of the product initially, so the way that this reaction had to change is it had to proceed in the forward direction. It's the only way it could have went. So that means this one had to decrease, and this one's going to have to increase by a corresponding amount. So if I take those two things and subtract them, the difference is 0.0028 molar. So that represents the amount that this one went down. Okay, so this is my change. And if I want to relate that based on a 2-to-1 stoichiometry, how much did this one go up by? 0.00 what? If there's 2 of these consumed, remember 1 produced. 0.00. 1.4, exactly right. Okay, because I took 2 of these guys for every 1 produced. It increases by that amount. So that means at equilibrium, this one's 0.0014 molar. So now I know the equilibrium concentrations of both species. It's a simple matter of plugging those into the expression for K sub C. And this guy is, K sub C is products over reactants. So it would simply be the concentration of the N2O4 divided by the concentration of NO2. You got to remember to square it because of the 2 here. So I can plug the numbers in and find out what that value is. So on this example, we figured out these concentrations already. We said the change in concentration of the reactant was it went down by 0.028. That meant the change in concentration of the product was that it increased by 0.0014. That allows us to calculate our final concentrations. So products over reactants, the only thing I have to do is plug in my values for K sub C. K sub C, put in the concentration of the product. Sorry. Put in the concentration of the product. The concentration of the reactant, square it. I get it, that's 4.7.
Why do you have to square it again?
Okay?
Because that's just a part of the...
Because of the stoichiometry here. So products over reactants raised to the power of their stoichiometries.
So whatever number's in front of that one?
Whatever number's in front. If it's 1, it's to the 1 power. You don't have to do anything to it. But if it's a 3, you have to take it to the cube. If it's a 1/2, you have to take the square root of it.
Same top.
Yes, top and bottom. Yep. Okay? So, question on that. If we want to calculate K sub P, the formula for K sub P, we've already talked about this, is K sub C to the RT delta N power. If I look on this one, I've got 1 minus 2, so the value for delta N is a minus 1. So it would just be the value of R. Take the temperature from Celsius to Kelvin, 373. So we could plug it in and we could find out what the number would be. 0.15 if we want to calculate K sub P. But we've already done K sub P calculations. We're going to use this to find values. Okay, let's look at the second set of numbers. So the second system on this one had the concentration of product. I'll change this one to blue at 0.02. And then at equilibrium, we know how much of that product's left. So 0.00452. So let's look at the change that occurs with this one. So I'm going to use my eraser and just change these. If I could get it to erase. There we go. All right, so now we had a amount of the product. Now there was none initially of the reactant. The product was 0.02 molar. And I looked how much of that product's there at the end. It's 0.00452. All right, so at equilibrium, 0.00452. Now on this one, since I'm only starting with the product, the reaction has no choice but to go in the reverse direction. It can't go forwards. There's no reactant for it to react with. So this number has to be decreasing, a negative. This one has to be increasing, a positive. All right, so if I subtract those two, I get that it decreased by 0.103 or 0.1055. 0.1055 molar. So what would be the change over here? That one's decreasing, this one's increasing. How much would it increase by?
You double that?
You double it, exactly. So at equilibrium, have that amount. Okay, so let's go now and plug those into our K expression. So products over reactants. Square it. And I get 4.7. What did we get a while ago? For the first system, 4.7. So it doesn't matter which system you start with, whether you start with experiment 1, where you're starting with reactants, or you start with experiment 2, where you're starting with products as written. At equilibrium, both of them are going to go to exactly the same places. It doesn't matter which one you start with. Both of them are going to end up at 4.7 for K sub C. Okay? So it doesn't matter if I know something about the products at the end or something about the reactants at the end. As long as I know one thing, okay, I can relate it back. Simple enough? These are tough. Okay? I'm not going to lie to anybody and say they're not. You really got to think your way through these. Okay, so the reaction quotient is where we can look at a system and we can use this to determine which way the reaction is going to go, which direction it's going to proceed. Is it going to go in the forward direction or is it going to go in the reverse direction? And the way that we do this is we compare the current concentration ratios to what it is at the equilibrium constant. So we calculate what we call Q, the reaction quotient. So we've got it down here at the bottom. And we compare the value of Q to what is the K sub C. What this is it works the exact same way that we calculated K sub C. We just did in the previous problem. What we do is take the current concentrations, we take the constants, products over reactants, we raise it to the power of the coefficients just like we did for the products and reactants with K sub C. And we just want to look at the value of Q and compare it to K sub C. We want to see which one's the largest. What happens is that, and when we look at the system, here's just our example. Same thing, products over reactants. Put the products over the top, raise it to the respective powers. Products CD over reactants AB. If it's a gas phase, you can do a Q sub P for the gas phase, like K sub P, and do the comparison. But what we want to do is compare K sub C or K sub P to this Q value that we've just looked at. And we want to see which one's the biggest. Okay, so if Q that we've just calculated is greater than K, that means the reaction is going to proceed fastest in the reverse direction. So if Q is greater than K, the reaction is going to proceed towards the reactants as written. Okay, it's going to go backwards. All right, now the opposite's true. If Q is less than K, it's going to proceed forward fastest in the forward direction. It's going to increase the amount of products and decrease the amount of reactants, so it's going to go forward as written. So this is what we can use to figure out, is it going to be pluses or minuses when we set up the ICE table? Is it going to go forwards or is it going to go backwards? If it happens to be a situation where Q is equal to K, that means the system's already at equilibrium. There's not going to be any net change. Okay, so you're there. There's not going to be any change that's going to occur. Now we know in a system that if it just contains reactants, so if we set up the ratio and divide it out, that means that Q is 0, there's no choice. It's got to go in the forward direction. So anytime you just start with reactants, it's got to go in the forward direction. And the opposite is true. If I just start with products, that ratio would be affinity, and affinity is greater than K. So then it's going to go in the reverse direction. If it just start with products as written, it's going to go in the reverse direction. Now, we talked about how we could take a reaction and we could reverse it around. So instead of in this one going A yields B, what if I wanted to write the reaction B yields A? How could we calculate the difference in K? Remember this from last Wednesday? Do what? We flip the value of Q. Yep. So if we want to spin a reaction around, we just invert the value of K or Q. Okay, so if something's written the other way, no problem, we can deal with it. All we have to do is invert the value for the equilibrium constant. Okay, let's put this to work to figure out how it's going to play. So this is a good slide to summarize these last few pages. If Q is greater than K, it's going to proceed from right to left. So it's going to go in the reverse direction. So Q is greater than K, it's going to go backwards. If Q is equal to K, the system's already at equilibrium, there's no net change. And if Q is less than K, it's going to make more products, so it's going to proceed in the forward direction as written in the system. So Q being less than K in that system. So if we think about what it's doing to go forwards, and we'll go back to slide. So if Q is less than K, as written, and if it needs to go forward in direction, what it's going to do is increase these concentrations. So these components are going to be going up, and these components are going to go down. What these ones on the top are going up, the ones on the bottom are going down. That's going to cause the value of Q sub C to increase to the point when Q sub C equals K. And at that point, the system's at equilibrium. So what it's doing is making this ratio mathematically what it needs to be by making more products consuming reactants in the system. That's what we're trying to look at. The value of Q just simply tells us, is it going to go forward or is it going to go in the reverse direction? Okay, let's do a calculation with it. All right, so I've got a system that initially It's N2O4. It's got 1/8 molar, and the product is N2O, and it's 1.28 molar. And I want to know which way the reaction is going to be. I'm going to go, and I've got the value of K sub C here. The equilibrium constant K sub C is 4.36 times 10 to the minus third. So it's products over reactants. So it's simply a matter of plugging in my my values initially, find out what the term is. So K sub C is the concentration of products squared divided by the reactants. So if I'm going to do Q, I'm going to do the exact same thing. I'm just plugging in my initial concentrations. So it's the concentration of NO2. So the NO2 is 1.28. Got to remember to square it because of the 2 stoichiometry, divided by the concentration of the N2O, and it's 1/8 molar. All right. So if I do that, I don't even have to do the math to know that this number is going to be bigger than 1. Right? Because this is, what was it, 10 something? I don't know. We'll divide it out. It's 30. Something with a decimal in there I can't read. It's 13.1. So 13.1 tells me that Q is now larger than K. So which way is it going to run? It's going to have to run in the reverse direction. So what it's going to do is decrease the amount of the products, increase the amount of concentration. Let's say that right? Yeah. Till it gets the ratio equal to this small, 4.63 times 10 to the minus third. Okay, so Q is greater than K. That means it's going to go in the reverse direction. That's simply the way that we use this. You plug in your current concentrations into the K expression, calculate Q, and you figure out, is it going to go forward, reverse, or is it at equilibrium already? All right. If you're given moles and volume, be sure to convert it to molarity first. Everything that we do in these values, it's molarity. Unless it's K sub P and it's the partial pressure of the gas and atmosphere. Exciting stuff. Okay.
So it's group.
It's group. For good or bad of it, it's group. Give a couple minutes. So the 2.3 is the value of K sub C, just to be clear. Couple more answers. They says we're either all going to float or all going to sink.
Get a boat.
Sometimes boats have holes in them. Okay, products over reactants. Concentration of B cubed by the concentration of A squared. Simply plug in our numbers. B is 0.05 cubed. A is 0.1 squared. And when I do that, I get Q is 0.0125. Anybody else get that? Okay. So now I'm comparing Q to K. In this case, the value of K is greater than Q. So if K is greater than Q, it's going to be this situation. The reaction is going to go in the forward direction to reach equilibrium.
Q is greater than K.
It's smaller
Wait,
than
K is greater than Q, and it's going to go left to right.
So K is,
K is the 2.3.
Yeah, and it's much greater than Q. So what did we note?
I voted C.
Okay.
We just forgot to do the cubed and squared, but it still worked out.
Yeah, in this case, it did, yeah, because they were so far separated from one another.
But we know now.
Okay, we live and learn. Question on this? All right, so when I get that test question, I'm going to expect 100% of you to get that one right. Okay. Now we move to what I like to call the challenging phase.
Now we
Now we're going to the challenging phase. So now we're going to apply this to systems where we're finding equilibrium concentrations when we're given the initials. So we're going to have to take and set up an expression mathematically given the equilibrium concentrations and K sub C value and find out what are we're going to be given the initials, and we want to find out what is, it's supposed to be a question mark, but it's a block. Find out what is the equilibriums in the system. So here's kind of our process that we do. We're going to set up an ICE table to figure out what we know. Then we're going to figure out which way the reaction is going to go, forward or reverse. So we're going to calculate Q and compare it to K, figure out direction. That's going to tell us what's going to be plus and minus. And then we're going to put in X to describe the change. Okay, there's going to be some relationship where something's going down and something's going up, and X is going to be that relationship. And usually I think of X as what it would be if it was 1 molar. Because if something was a stoichiometry at 1, that's the value we're going to put in for X. So what we're going to have for our changes are going to be X minus whatever there was initially, if it's a reactant, or X plus whatever's being formed, if it's a product. We're going to set up a mathematical relationship for X, and we're going to solve for X. If it is a second order equation, what does that mean? That means I went back to high school. X squared, AX squared plus BX plus C equals 0. That's a quadratic. We're going to solve the quadratic equation, which many of you haven't done since high school. Okay? We can solve the quadratic. If we get lucky, we can take a square root of both sides. Much easier. If it's not, we have to deal with how we make an approximation to solve for something, and we can do that by looking at the value as K sub C very large or very small. Used to the method of approximations was something we relied on heavily. Today in the upper level courses, I don't even teach approximations because we have programs like Mathematica that will give us exact mathematical solutions as quick as I can type them in. So it doesn't, we solve systems that are 5 equations, 5 unknowns, a fifth order polynomial. And you use matrix algebra, that used to take hours to solve something like that. Now it's as quick as you can hit shift enter. So the emphasis on using approximations, we see it for simple systems. We don't have to worry about it as much as we used to. Our key thing that I want you to be able to do is set up the system of equations. All right? That's where you get half your points. So when we simplify things, here's how we do the simplifications. If the equilibrium constant is very small, that means that it favors the reactants. It's not going to go forwards very much. If it's very large, initial concentration, and it doesn't go forward very much, that means there's not a significant change to reach equilibrium. So what I can make the assumption sometimes is that the equilibrium concentration of a reactant is equal to the initial concentration less whatever the change was. And if this number is really small, that's almost the initial. So I can make the assumption sometimes that the equilibrium concentration is equal to the initial. If it's a small value of K, what's small? Less than 1 times 10 to the minus 3. That'd be my only time I'd want to consider using that. So we always have to check if it's valid to make assumptions. You all know the acronym for what happens when you make assumptions. Same thing here. We have to make sure the change that we're suggesting is really valid, so we compare our approximations to what the actual change is. And we look at the ratio as the approximate value divided by the initial concentration. Is that less than 5%? And if it's, we call it the 5% rule. If that's the case, we consider that valid. Now, in some cases, when you're trying to get exact solutions in chemistry, 5% is a huge error. In many cases, 5% is a, woohoo, I'm happy with that error. Same thing when you do things in the lab. If you get a percent yield within 5%, that's usually high five time. If you miss it by 80%, that's you lost a lot of point time. Okay, so we set up the concept of disturbing an equilibrium. The system's going to reestablish itself, restore the equilibrium. The thing that's going to remain constant is the equilibrium constant itself. It doesn't change. Whatever that value of K is stays the same in the system. So what changes is the concentration of the chemical species are going to change until K is restored. The new concentrations are going to be different, but that value of K is still going to be exactly what it was. The only thing is that if you change the temperature, K is temperature dependent. If you change temperature, you change K. Okay, so I'm going to work through one freehand first, and then we're going to go backwards, and I'm going to do the next one using the ice system. All right, so way that you may look at it if you were to do it. So my problem has, I've got a sample of phosphorus pentachloride, and I put it into a container of ½ liter. It's heated to 160 degrees. It tells me it decomposes into the products PCl5 and Cl2. So my reactions that's occurring is this guy. PCl5 decomposes to PCl3 and chlorine gas, Cl2. And it tells me at equilibrium the amount of moles of the products are both 0.0 or 0.203 are formed of each, and it tells me the value of K sub C. Okay, so if I'm going to set up my system to study this, I don't know how much I had initially. Right? I know there wasn't any of these guys. So on this one, it tells me what is the concentration of these products. Now, do I know the concentration? Is that what's given to me? What I know is the number of moles. It tells me it's in a ½ liter. Okay, so it says it's in a 500 liter container, or 500 milliliter container, ½ liter. So if I divide those each by ½ liter, it's 0.406 molar. So in this case, I know the K sub C expression is known. I know what K sub C is. It's products over reactants. So it's the concentration of the PCl3 times the concentration of the Cl2 divided by the concentration of the PCl5. Okay? Now, what do I know in this? I know, at this point, I know what K sub C is. Right? That's given to me. I know the concentration of PCl3 at equilibrium. I've got it. Cl2 at equilibrium. I've got it. So this one's a pretty simple one. All I need to do as far as rearrange this and solve for what I don't know. So I'm going to find out what is the concentration of my unknown in the system. So PCl5 concentration is equal to the concentration of PCl3, which we said was 0.406, times the concentration of Cl2, this guy, which is also 0.406, and divided by, I'm going to cross multiply, so this guy went to the top, that means this one goes to the bottom. K sub C is going to go on the bottom, 0.0635. So, just a plug and play. .6 molar is the equilibrium concentration of the PCl5 gas. Because we knew all the other concentrations in the system at equilibrium, we didn't even have to use anything in the ice table. That's the great one. If you get this problem, they don't always work like that. Okay, question on this one before I got to do one more complicated. All right, let's step it up a notch. Okay, so on this one, we're going to work it with pressures instead of concentrations, and we've got K sub P given to us. And we're going to solve this whole thing in terms of K sub P's. So I2 plus Cl2 yields 2 ICLs. Okay, so it tells me the value of K sub P. K sub P is this value of right at 82, a little bit less than that. All right, it tells me the initial pressures of all the gases are 0.1. I want to know what are the equilibrium concentrations of everything. All right, so if I think of my ice, there is 0.1 of everything. So first thing I need to do is figure out, is the reaction going to go forwards as written or is it reverse as written? So I'm going to figure out what is the Q. So Q is products over reactants. So the concentration of the partial pressure of the ICl2 squared divided by the concentration of the partial pressure of the I2 and the Cl2. Well, everything's 0.1 squared divided by 0.1 and 0.1. Q is just simply equal to 1. But now I have to compare Q to K sub P. And what I have in this case is Q is less than K sub P. So if Q is less than K sub P, it means the reaction is going to proceed in the forward direction. So that means that the products that are going to be formed are going to be positive. This is going to be a positive term, and these are going to be negative terms. So what I'm going to do is define the changes that are going to occur in terms of X. Everything here is one-to-one stoichiometry, except at the end, this guy is 2. So if I look at the change that's going to occur, I'm going to make this one minus X, and plus 2X. Okay? So now what I have at the end is 0.1 minus X, 0.1 minus X, and 0.1 plus, write it, 0.1 plus 2X. I simply plug in these values, simply plug in these values into the K expression, products, reactants, and a finite X. Trivial. Well, sometimes not so much. So we're going to do exactly that. Minus x plus 2x, 0.1 minus x, 0.1 minus x, 0.1 plus 2x. Golly, we hadn't done algebra forever. We forget it. So on the top, K sub C is the concentration of the P IC. Okay, this guy, I've got to put it in there, and I've got to square it. Got to expand that term. Y'all remember how to do that? All right, on the bottom, I've got 0.1 minus x and 0.1 minus x. Now, because the terms on the bottom are the same, it becomes 0.1 plus 2x squared over 0.1 minus x squared. And the thing I've got common is I've got the square to both sides, the top and bottom. So I can factor that square out. So it's going to become, take the square root of both sides. So take the square root of K sub C, gets the square rid of that square root. So the square root of K sub C, and now I've just got this term over this term. I'm going to do the algebra to rearrange and solve for what x is. So I'm going to take this term on the bottom, and I'm going to multiply it over to this side. So I'm trying to isolate x, and when I do, I've got K sub C times the term that was on the bottom. 0.1 minus x is equal to 0.1 plus 2x. Now I distribute my K sub C term to both. All right, so K square root of K sub C times the 0.1, square root of K sub C times the minus x. So now I take that and rearrange for what x is. So I put the x's on the same side. So I took this x that was a minus here, moved it to the other side. Now it becomes positive. The 0.1 that was a positive on this side, move it to this side, it becomes a negative. So now when I put those two together, I've got on the left-hand side the square root of K sub C times 0.1 less 0.1, and that's 0.805. And I've got 2x plus 81.9 times x, which is just a hair over 9. So that's 9.05 plus 2 is 11.05x. Solve for x. X is 0.0729. Okay? Didn't even have to do a quadratic equation. But now I know what x is. I know what this number is in both cases. So I can plug x in, and I can apply that to every one of these. So if I know what the value of x is, apply it to my systems. So I've got 0.01 less x. That leaves me with the I2 of 0.027. If I want to know how much CO2 is there, 0.01 minus x, same amount, 0.027. And then how much product is there now at the end? I started with 0.1, I add 2x to it. When I add 2x to it, I end up with 0.246. So now I know what are the equilibrium concentrations of every species in the system. No one knows. That's hard. I mean, that's a lot of, individually, you should be able to do every one of those steps, but putting the whole picture together is what takes practice. Okay? So I'll tell you, if this is something that just, it's impossible for me to do, you know, some people are, I'll use the term math phobic, we don't like it. But if we can get this to the point where we're here, that's half the points with me. Okay, partial credit rules. If you can get to set the system up here, so if you can write this part of it out, set up the ICE table, figure this out, apply it, set up the K sub C, I'll give you at least half the points on the problem you have to do. All right, so where are you going to have to use this stuff again? Organic, probably not once. If you take chemical analysis, every day. Biochem, every other day. So equilibrium is something that we have to understand, and we have to be able to set up systems and solve for these types of things. So if you're going to take advanced classes in chemistry, if you're a pre-med, pre-professional, whatever, pre-dental, pre-optometry, you need to invest the time to learn how to do these things. If you're not ever going to apply another higher level chemistry course, you might study something else more. Okay. Question on this before I go forward. These are problems, literally you'll invest 10 minutes minimum in each problem. They just take some time to set up and to work out. Okay, let's see, is it y'all's turn? I can't get it to go forwards. Get it over here. Keep going backwards. All right, so here's one of my problems. So now this system, we've got a K sub C given to us. So K sub C is 1.1 times 10 to the minus third. And this is the decomposition of molecular bromine. See, Br2 decomposes to 2 Brs. So usually bromine, the molecular form's stable, but if you heat it up to 2800 degrees, or to 1280 degrees, it will decompose. It'll break apart. But still, this is not a big number, so if it's less than 1, it means it's not very favored. So just a little bit of it's going to decompose. So it tells me the initial concentration in this system of the bromine is 0.063, and of the monoatomic bromines, 0.012. I want to know what are the concentrations at equilibrium. So let's set the system up with the ice. Reactants, products, okay? The initial concentration of the reactant, the initial concentration of the product. The change, I'm always going to define it in terms of what's the stoichiometry of 1. So there's only 1 here, so I'm going to put this one minus x. Because there's 2 here, this is going to be plus 2x is the change. So at equilibrium, what I have left is 0.063 minus x. For the products, it's 0.012 plus 2x. So I take the K expression, products over reactants. K sub C. Concentration of the products squared divided by the concentration of the reactants. And I know the value of K sub C. It's my 1.1 times 10 to the minus 3. So I know that term. What I'm going to do is simply plug in the concentration of the products. So the products were the 0.012 plus 2x. Got to square it. Divided by the concentration of the reactants. 0.063 minus x. And find x. This one's not so pretty. There's not a simple square root function that you can take for it. So when you solve for this guy, you rearrange it. You have to now solve for this guy. I'm going to let you do the math. You expand this, and then you're going to take this term, multiply it to the other term, and rearrange it for x. You get 4x squared plus 0.048x plus 0.000144 equals this term minus x. You rearrange it in the form of quadratic. What the quadratic is a x squared plus bx plus c. This is my a term. This is my b term. This is my c term. We solve our friendly quadratic equation. Negative b equals the square root, or equals plus or minus the square root of b squared minus 4ac divided by 2a, something every one of you have seen at some point. And when you plug in the values for x, you'll find that x can either be a minus 0.0105 or it's a minus 0.00178. And if I go back and look at these values, plug out what x is, the change in x and the plus 2x, we'll find that one of them is not possible. So if I plug in the first one, what happens is that the concentration, plugging in this term, I come up with a concentration of negative 0.009. Can't ever have a negative concentration. So that tells me that this is not the real root. Now I use this one as my real root. This is the good guy. When I do that, I find the equilibrium concentration is the minus x. This point 0.0648. That's a nasty problem to solve. I will not give you something that nasty.
Yeah.
Okay? But I managed to solve it quadratic. This one's got a lot of work on the front side of it. Okay, we'll do some more of these, and I'll show you more examples of what we need to learn tomorrow in class. Start working on some of these guys. They're hard.